Okay, so we'll continue with the more general analysis of the randomized incremental construction. So we started with the example of quicksort. Okay, that was in a very limited context where we dealt with only points and intervals. But in general, what I said was you have this notion of objects and ranges, right? Objects and ranges. So the randomized incremental construction can be viewed as maintaining relationship between objects and ranges, and this relationship can be quite general. It need not be a 1:1 graph, and as you keep on adding objects, some of these intervals, they are removed, not intervals, I mean in general ranges, and some new ranges are created, okay, and thereby you are going to add the new edges are created in the graph, okay, because of these additions, and we keep track of this changing graph, and eventually when we have added all the objects, the final so this is called a conflict graph, right. So the final conflict graph okay, that basically corresponds to the solution of the problem. Right. So, and all and what we obtain as intermediate steps, so that we have to analyze. Okay. So, the intermediate graphs okay, will determine the overall running time. Right. This is what we observed, and the expected running time we argued was proportional to expected running time, which is essentially taken over all possible permutations, okay, averaging over all possible permutation, all possible, let us say, insertion sequences, okay, that we argued was equal to the for all steps I, okay, the number of new edges created. Right. Last time, and in the case of quicksort, we argued that this quantity was something like 2 over I for each object, right? And since there are n objects, so this is for we argued rigorously for quicksort, right? So this was bounded by this quantity, and therefore the whole thing was bounded by n times 2 over I, roughly about n log n. So this was how we concluded the analysis of quicksort. Right. Now, in general, I said the objects in quicksort were points and the ranges were intervals. Okay. In general, the objects could be anything and the ranges would depend on the context of the problem. Okay. So let me now just draw your attention to the notations or some of the definitions that we will be using to do a more general analysis. So, we want to do a very general analysis of this entire process of maintaining this graph, okay, over a sequence of insertions, and at each step we will try to, when we analyze, we will try to bound the number of expected number of new edges created. Right. So that's basically the strategy for analyzing the general randomized incremental construction, right. And this clearly should depend on the problem. Okay. So, this should depend on the problem, the specific problem, and therefore, if we for a specific problem we should be able to just plug in this bound and get the final figure out of it. Okay, that is the goal. So, it is a very general. So, the randomized incremental construction itself is a very general construction procedure that can be applied for any all kinds of geometric problems or even non-geometric problems, but it has been mostly studied in the context of geometric problems. And then if we can get a bound, so this analysis is also very general, and if we can get a bound for a specific problem, then we can just plug in that figure and get the final expected running time. Right. Okay, so what are the notations that we need? So, n is a set of objects. Okay, so capital N is a set of objects, and small n is the cardinality of that. Sigma is what we are calling a configuration. Okay. So, sigma is a configuration, right, which is going to be defined by some objects, okay, and the set of these objects I am calling D of sigma. Okay. So, in the case of something like quicksort, okay, sigmas are defined to be intervals. Sigmas are intervals, okay, and an interval is defined by the two endpoints, right. So, it is basically a pair of points, pair of input points. Okay. So, this is defined by some objects. So, suppose this is some sigma. On the other hand, L sigma are all those objects, the set of objects intersecting sigma. So, if you consider all the points on the line, okay, this specific, if I am considering this specific interval, then these two are the defining objects of the interval, okay, and the red points basically corresponds to L sigma. We make this further assumption that D of sigma is bounded by a constant. So, we do not want to get into a situation where an object a configuration is defined by an unbounded number of objects. So, in the case of intervals it is 2, okay. For we will see some other examples where it may be 3 or 4 or 5, but it has to be some kind of constant. Okay. So, that is our assumption, and it is valid in most situations. And the other thing, this is kind of technical, so let us not worry too much about it. Valence is the number of configurations associated with the same set of objects. So, it is not clear in the context of quicksort how the same set of points can define more than one interval, okay. But I will just show you an example where this is true, but let us not get into why this is important. So, this is called the valence, and we are saying that again even if there is more than one configuration associated with a set of defining objects, there cannot be too many such things. Again we are saying the valence, that is what we are calling valence, and valence itself is constant. Okay. But I am saying this is kind of technical, let us not get too much into that. So, let me give you another example. This is a purely one dimensional case, so it is kind of trivial, we did not even need the definitions, but let us say something like the trapezoid, the visibility map problem. So, in the visibility map problem, what are you given? A set of non-intersecting line segments, okay, and you draw the vertical lines to the endpoints and extend them till they hit something above or hit something below, okay, and those define the trapezoids. Okay. So, these are the trapezoids. Okay. So, when I extended the vertical lines to the endpoints, this is what I get. So, this blue shaded figure is a trapezoid. Now, we have already observed that for this problem trapezoidal maps or vertical visibility maps, okay, what we observed is that, so sigmas in this case are trapezoids. Okay. So, we are in the context of the problem of trapezoidal maps, our sigmas are trapezoids. Okay. And so, d sigma is a set of line segments, defining the trapezoid, defining the boundaries of the trapezoid. So, how many what is this thing then, the maximum size of d sigma? We actually went through this. Does anyone recollect? 4, exactly, good. So, we observed that there can be many kinds of this trapezoid. So, one kind of trapezoid like this, where essentially this trapezoid is being defined by just this and this. It is sufficient. So, it's just these two segments define this trapezoid. Let's say tau 1. Okay, but you can also notice here's another thing I will draw your attention, that something like this let us say tau 2 and this tau 3, these are also trapezoids, okay, which can be defined with the same line segment, right. Maybe these are unbounded or something, it can be like this. Okay. The other segments are lying somewhere here, there. Right. So, you can see, so this is what I was calling as sort of defining as valence, that there can be more than one trapezoid defined with the same set of line segments, so same set of objects, but there can't be too many such things. Okay. For the same set, these two line segments, we have 1, 2, 3 such possibilities, and you can argue that there won't be more than constant number of such trapezoids defined by the same set of line segments. Okay. But then again, I will leave this aside right now. No, let us not worry too much about the valence part. Okay. So, this is one kind of trapezoid, and the reason why this is 4 is essentially because of a configuration like this. So, this configuration is defined by 1, 2, 3, 4 line segments. Okay. So, this trapezoid, let us call it tau 4, is defined by this. In fact, this blue shaded trapezoid is one such example. It is defined by 4 line segments. Okay. But these are not the, so there are other kinds of trapezoid. This trapezoid has a particular property, okay, and the property of this blue trapezoid, what's the difference between this green shaded trapezoid and the blue trapezoid? Yeah, the blue does not contain any other line segments, right. So, so L sub sigma is the set of line segments that intersect sigma, line segments or objects that intersect sigma. So, in this case, the blue, if you look at the blue shaded trapezoid, okay, L sigma is basically empty, for the blue one. Okay. And whereas, if you look at the green one, okay, so let us call this L sigma blue and L sigma green. So, that has 2 intersecting objects or intersecting line segments. So, L sub sigma, the cardinality of that is 2. Okay. Okay. I will skip. So, this was an example from Voronoi diagram, but for the timing I will skip this example. Why is it 2 and not 3? Let us go back. Why do you think it should be 3? The number of objects that intersect it, not leaving aside the defining objects, not including the defining objects. So, I will skip this example of Voronoi diagram. Okay. So, continuing with the definitions. So, what is being said here is this pi of n is a set of all configurations for a given set of objects. Okay. So, pi's of n is the set of all sigmas. Okay. So, these sigmas, it may be like the green one or the blue one, it may be empty, it may be non-empty, whatever. So, this entire set we are defining as pi of n. Okay. On the other hand, pi I of n is a subset of pi n, okay, where L sigma where sigma belongs to pi y I of n if L the size of this conflicting objects is equal to I. So, in the previous example, the green trapezoid or the green sigma, okay, would belong to pi 2 of n, right, whereas the blue one was pi 0 of n, because there are no conflicting things. Okay, now R is a subset of n. Okay. R is a subset of n, which is, let us say, in most cases typically R is a random sample. R is a random sample. So, then pi 0 of R, okay, are all those sigmas that are feasible in R. Okay. So, what is feasible in R? If the defining objects belong to R, only then it is feasible in R. If I take a subset, okay, if I take a subset, so I have these these line segments, okay. There are many such trapezoids defined by this. Okay. If I pick a random sample, suppose sample any subset basically, okay. So, then this particular trapezoid is feasible in R, because the defining segments also belong to R, okay. But something like this is not feasible in R, because the defining for this trapezoid, this was one of the defining segments and this does not belong to R. So, this is not feasible in R. So, some of these trapezoids will be feasible in the subset only if the defining objects are there, okay. And moreover, since I am writing 0, it will also implies that is the same thing, like it was pi 0 of n, this is pi 0 of R. So, inside R, okay, so implies that for this sigma, okay, there are no objects in R that intersect sigma. So, what have we defined? We have basically defined a configuration which is defined in terms of some constant number of objects. Okay. For a given configuration sigma, what are the defining objects? What are the conflicting objects? D's of sigma, L's of sigma. Pi's of n is this entire set of configurations, okay. And then pi of n are those configurations for which L sigma has size I, okay. And whenever we restrict it to a subset, then we have a notion that certain configuration is active only if the defining objects are in that sample. Okay. So, these are the things that these are only things that you need to basically remember, but in the beginning you may have some there may be some confusion with the notations. So, here is an example. So, the red segments are basically R, okay. And so, if you look at A, if you look at the trapezoid A, this trapezoid belongs to pi 0 of R. Red is a sampled set. Right. So, it has no conflicting objects that belongs to R, but it has some conflicting objects that belong to the original set. Why are we doing it? One reason that we are trying to define all these things is if one were to, in some very generic sense or very general sense, construct, let us say, the trapezoidal map using some kind of divide and conquer. Right. So, in 2 dimensions it is not clear how do you actually divide the problem. Right. So, one possibility is that we pick a sample, okay, and based on the sample we define these trapezoids, okay, and these trapezoids will basically be the subproblems. Why? The trapezoids that belong to pi 0 of R, okay, they will have some conflicting objects from the original problem, okay, and then we can actually solve the problem restricted to the trapezoid. So, like we can solve recursively all the segments that intersect trapezoid A. Okay. And it's a visibility, vertical visibility problem. So, we are not losing any information. So, within that trapezoid, we will do some kind of a recursive call, and then what would you really, what is desirable? What is desirable is that for any divide and conquer, that the subproblem sizes should not be too large. Okay. So, if I pick a sample of, let us say, size r, okay, ideally I would like to have a subproblem of size n over r. Now, that is easy to visualize in the case of one dimensional problem. Okay. I pick up r samples. Okay. If I pick them, if I pick them exactly equally apart, there will be n over r points in each of the intervals. Okay. It is not at all obvious in the case of a higher dimensional problem that what is those exactly equal, what there is no ordering. So, the reason why it is so simple in one dimension, also natural, because there is a natural ordering in one dimension. For a two dimensional problem like trapezoidal maps, we do not even have a notion of ordering. How do you order things in two dimensions or higher dimensions? Okay. But we are still trying to define some notion of dividing the original problem into some subproblems, such that each subproblem should have a bounded size. Bounded means something, if I pick as if I want to divide into r parts, roughly each subproblem should have what n over r size.
So, in one dimension, when you are talking about intervals, the size corresponds naturally to the length, right? But in this case, what will be the corresponding size? For example, in this.
No, the size corresponds to what length? We are not talking about lengths. We are talking about the number of points in an interval.
Length, number of points.
Yeah. So, here exactly. So, now L sigma is basically the subproblem. If sigma is a subproblem, if sigma belongs to pi 0 of n, pi 0 of r is a subproblem, then the natural thing is that all those objects that intersect sigma defines a subproblem. So, these two blue segments that intersect trapezoid A is precisely the subproblem, right. So, now there is a difference between A and B. Can you sort of tell me what is the difference? Both of them have some conflicting segments, but there is a difference.
One and B, or everything is contained.
Exactly. So, the subproblem B has segments that only lie within B, whereas the subproblem A, if you are defining that trapezoid as a subproblem, that has these two line segments which also intersect other trapezoids. Okay. So, this is the case that I was pointing out, that in the case of when we are analyzing this conflict graph, each object could belong to only one interval in the case of quicksort. But here, if these objects are now line segments, okay, and if the subproblems are trapezoids, okay, or the sigmas, then a single object, okay, can conflict with more than one sigmas. Okay. It can belong to more than one subproblem. So, you are not in that very simple situation where it is a one-to-one mapping. Each object belongs to only one subproblem. Now, in trapezoid B, of course, there is a nice case that these two belong to only B and nothing else, but in A, there are these objects that may belong to more than one trapezoid. And so, what happens as a consequence of this? What happens when you do a recursive call? What happens?
These are overlapping problems.
No, it is not overlapping problem. See, I can always clip this line segments to within the trapezoid. That is not a problem.
So, that the line segment which is trapezoid will be called will be processed.
Exactly. So, what is happening is that if you look at, so one aspect of divide and conquer that we normally tackle is the size of a subproblem. Okay. But the other aspect is what is the total size of the subproblems. So, we kind of assume that it is equal to n. But in a problem like this, or the way that we are trying to define the subproblems, you can no longer assume that the total sum of the subproblems is equal to n, right. So, it can increase because each object can conflict with more than one trapezoid, and when you sum them up, it is going to basically it can easily blow up. Okay.
But in normal divide and conquer, when you divide, you kind of partition it, right? I mean, So one subproblem does not have anything to do with separately solving.
Right, right. So that's what I'm pointing out. So, but you don't encounter these things, when you're only looking at these points and intervals and one-dimensional problems. But here, there is a clear-cut case for this, and for many other problems, we'll have this situation that the same object can conflict with many other, many configurations and can belong to more than one subproblem. Right? So there is a potential blow up as you go down in the recursion, which can cause inefficiency. Right? Okay, so let me just give you a very nice illustration of how random sample can be used to prove combinatorial bound. So, I am not even talking about algorithms now. Okay. So, suppose I was interested to count how many. So, okay. So, this happens to be a very important combinatorial problem. So, in the case of trapezoids, you can look at this quantity pi 0 of n. What is the size of this? That is the total number of trapezoids, right? This is the total number of trapezoids. This is empty trapezoids, right? Suppose I was interested in this quantity. Can you count this? The first one? Yeah. So, how many trapezoids can you create? Empty trapezoids. When you do this vertical visibility map. Say it again. Some order n. Clearly, it's a planar map. When we argued, in fact, I gave a figure probably like 6 times n or 3 times n or something like that. Okay. So, this is clearly order n. So, we know this basically from the fact that it's a planar map. Can you count this quantity? I am interested to know the number of trapezoids or get a bound on the number of trapezoids that have I intersecting segments. What is the total number of trapezoids without bothering about I? Right. So, if there are 4 segments defining a trapezoid, the maximum number of trapezoid is n to the power 4. So, a trivial bound for this is that this is less than n choose 4. Okay. But suppose I am interested in pi 2n or something like that. Maybe it's much closer to order n than n to the power 4. So, how does one even count that? It will really depend on my ability to sort of. So, this is a purely combinatorial problem. How do I draw those trapezoids so as to maximize this quantity? Okay. So, this is worst case. This is worst case over all arrangements of line segments. Yeah, so, what can you say about this?
You take I segments, choose that with the NCI, you remove them, assuming that they would be the intersecting lines.
How can we assume that?
That would be the maximum.
Okay, so let me not even. You can think about it offline. Let me give you a very simple way of proving this bound. Okay, so there are just a few lines of proof. Let's go through that. So the claim is that pi I, or I have written here a. So pi I, if I write it as I, pi I of n, the size of this, okay, is bounded by big O of 2 to the power I plus d, expectation of pi 0 of r. Okay. R is a random sample. R is a random sample of size n over 2. Okay. I've deliberately picked a random sample of size n over 2. Okay. So, this quantity expectation, when we pick a random sample of size n over 2, now this is a very general bound. This doesn't talk. This is not just limited to trapezoidal maps. Okay, this is for other kinds of problems also. If it is trapezoidal map and you pick a sample of random subset of size n over 2, what is the size of pi 0 r? Pi 0 of n over 2. Order n, right, n over 2, some order n. So, this even this expectation actually it does not matter. So, it is actually this is always less than some constant times n over 2. Okay. D is the number of objects defining a configuration. Okay. So, this is the maximum number of objects defining a configuration, any sigma. Okay. So, mostly as I said it is going to be constant. So, D is order 1. Okay. So, this quantity big O of 2 I plus D, okay, if D is a constant, okay, and I is also a constant, then it follows that if I am interested in this pi 2 of n in the case of trapezoidal maps, this whole thing is again order n, if you have to believe this claim. D is constant because there is a maximum number of objects defining any configuration is 4. Suppose I choose I to be equal to 2, that is the quantity I was interested in, pi 2 of n, okay. And pi so this is 2 to the power some constant which is constant, and then we argued that E expectation, it is not just expectation, in the worst case also it is less than c times n over 2. So, this whole thing right hand side is big O of n if you are looking at pi 2 of n for trapezoidal maps. So, it is actually what we suspected, that it is actually linear and not n square or n to the power 4 n cube, nothing of that. Okay. And why is that? Why, how can we claim this from a random sample? Okay. So, that is what this proof is. So, one way of describing pi 0 of r, okay. So, r is a random sample, okay. R is a random subset of n. Okay. So, what have I written? I have written pi 0 of r, okay, is I sigma r, okay, and sigma is the set of all configurations of the n objects, and this I sigma of r equal to 1 or 0 depending on whether sigma is feasible in R or not feasible in R. So, if it is feasible in R, then we are saying that we will count that trapezoid. If it is not feasible, then we do not count that trapezoid. That is it. It is just a this is called an indicator function. Right. Now, I take the expectation on both sides. See, this is for a specific subset R, but I am choosing R to be a random subset, right. So, I will take an expectation, I take expectation on both sides. Okay. So, if you take then I can expand this using the linearity of expectation, okay, and this is nothing but the probability that sigma belongs to okay. So, if you go through the next couple of lines of the proof, what does it say? So, E of pi 0 r is this, just what I have written, this is probability of this, and then this quantity. So, instead of summing over all pi's of n, okay, if I sum only over pi I of n, okay. So, since pi of n is greater than that, so I can say this is, if I just restrict my summation to pi I of n, okay. So, this will be greater than or equal to that, right. So, that is all the proof is about. Okay, this is E of pi 0 of r, this quantity, this summation. So, pi a of n, that is the right hand side, is greater than or equal to pi a of n times, why did I write this 1 over 2 to the power a over d? Okay. What is this quantity? So, why is this probability 2 to the power a plus d? Every object is being chosen with probability half. Okay. So, probability that sigma belongs to pi I n is belongs to pi 0 of r means that we have chosen all the defining objects, all the d defining objects, okay, and not chosen any of the I conflicting objects. So, therefore, that probability is 1 over 2 to the power a plus d. The last line. So, this quantity I am claiming is this quantity. Right? Why is it that? So, what is the probability that sigma belongs to pi 0 of r given that sigma belongs to pi I of n? It means that that particular configuration is feasible in R, means we have chosen all the d defining objects, okay, and we have not chosen any of the I conflicting objects. Sorry, A actually, I am using A here. So, well, I or A, sorry. So, this would be I, sorry. So, that is 1 over 2 to the power I plus d. Right, all the I plus d has to be chosen. Yeah, right. And so, I will stop here today, and the beauty of this proof is that this is a combinatorial bound, okay, that is completely independent of any kind of probability. I have just used linearity of expectation to prove this bound, but this bound holds for any configuration of line segments. Okay. So, and this method, in literature is called the probabilistic method.